In the physical universe, the idea of nothing may only exist in theory, not in reality. Even if we remove all energy from the universe, it doesn't become truly empty. Currently, the universe seems filled with various things like matter, radiation, antimatter, neutrinos, and mysterious dark matter and dark energy. Even if we were to take away every bit of energy, the universe would still create new forms of energy. Why does this happen? It's like the universe itself doesn't understand our idea of nothing at all. If we were to eliminate all energy, leaving only empty space, we might expect the universe to be at absolute zero, with no particles. Surprisingly, that's not the case. Even if we artificially make the universe appear empty, its expansion would still produce radiation. This continues into the distant future, or even back to the time before the hot Big Bang. The universe, it turns out, never truly becomes empty. With all of this, is it really possible that the universe really came from nothing? We are certain that something always exists. Even if we remove particles, antiparticles, photons, and quanta from a space, empty space still remains. If we move far from any mass or energy sources, clear the space of external electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a kind of physical nothingness still exists. In this empty space, quantum fields persist. The fundamental constants and laws of physics remain. There is a zero-point energy inherent in that space with a finite positive and non-zero value. This seems to be the closest we can get to nothing within our universe. While you might imagine an even more nothing-like state, it doesn't have a physical reality. No experiment can create such a condition. Stick to science, and we can say that something always exists because true nothing cannot coexist in our universe. However, when it comes to the question of why this is the case, science currently has no answer. Here in our universe today, it's very clear that space is anything but empty. In every direction we look, we see stars, gas, dust, other galaxies, galaxy clusters, quasars, cosmic rays, and even radiation both from starlight and left over from the Big Bang itself. If we had better eyes, or let's say superior tools at our disposal, we could also detect the signals that we know ought to be out there. This includes gravitational waves from any mass accelerating through a changing gravitational field, the elusive signals from whatever makes up dark matter, and a more comprehensive view of black holes, both active and dormant, beyond those emitting the most radiation. Everything we observe happens in a universe that isn't static, but is continually evolving. From a physical perspective, it's fascinating to understand how our universe is changing. On a large scale, the fabric of our universe, known as space-time, is expanding. This means that if you place 2 points far apart in your space-time, the proper distance between those points, the time it takes for light to travel between those points, and the wavelength of the light traveling from one point to the other, all increase over time. The universe isn't just expanding, it's also cooling due to this expansion. As light stretches to longer wavelengths, it moves towards lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. Throughout this process, objects with mass or energy in the universe are attracted to each other, forming clusters and creating a vast cosmic web. If you could somehow eliminate it all the matter, all the radiation, every single quanta of energy, what would be left? In a way, you would have empty space itself, still expanding, still following the laws of physics, and still subject to the influence of quantum fields that pervade the universe. This represents the closest physical approximation to a true state of nothingness, yet it adheres to specific physical rules. To a physicist in this universe, removing anything else would create an unrealistic state that no longer corresponds to the cosmos we inhabit. This implies that what we currently interpret as dark energy would still exist in this hypothetical universe of nothing. In theory, if you take every quantum field in the universe and set it to its lowest energy configuration, you'd reach the zero-point energy of space. This means that no more energy can be extracted from it to perform mechanical work. In a universe with dark energy, a cosmological constant, or the zero-point energy of quantum fields, there's no reason to assume that the zero-point energy would be truly zero. As the universe keeps expanding and cooling, there will be a far-off future when radiation becomes the dominant component, surpassing other forms of matter and radiation, with only dark energy being more dominant. However, there's another period in the universe, not in the future, but in the distant past, when something else dominated besides matter and radiation, during cosmic inflation. Before the hot Big Bang, our universe was expanding at an incredibly rapid and constant rate. Instead of being dominated by matter and radiation, the cosmos was governed by the field energy of inflation, similar to today's dark energy, but much more powerful and expanding at a much faster rate. If eternal inflation is correct, but time is still finite, where could the universe have originated? After all, there must have been a beginning, right? To tackle this question thoroughly, let's untangle three commonly confused concepts and discuss each one separately. The hot Big Bang, as it relates to our universe, the theory of cosmic or cosmological inflation and its role in preceding and setting up the Big Bang, the question of an ultimate beginning or origin for our universe, and why both inflation and the original idea of the Big Bang might not provide a satisfying answer to this question. In the early 20th century, a groundbreaking synthesis occurred as four crucial pieces of information, one theoretical and three observational, converged. Theoretical breakthrough by Alexander Friedmann, within the framework of Einstein's general relativity, demonstrated that a universe uniformly filled with any form of matter and energy cannot remain static and stable, but must either expand or contract. The rate of expansion or contraction is determined by the overall energy density of space. Henrietta Leavitt's observational work, establishing a relation between the period of brightening and faintening Cepheid variable stars and their intrinsic brightness. This is known as the period luminosity relation. Observations by Vesto Slipher measuring the shift in light, redshifted or blue-shifted, from our solar system's frame of reference in spiral and elliptical nebulae, later identified as galaxies. These observations indicated that these galaxies were receding from us at incredibly high speeds. Edwin Hubble, along with Milton Humason, identified the same types of variable stars that Henrietta Leavitt had studied in those spiral and elliptical nebulae. This allowed them to measure the distances to these galaxies and confirm their extragalactic nature. The combination of these four pieces of information led to the formulation of the idea of the expanding universe. If the universe is expanding, it implies that as time progresses, space itself expands. Consequently, the matter within the universe becomes less dense because although matter consists of a fixed number of particles, the volume it occupies increases as space expands. Therefore, the universe becomes less dense over time. Radiation, such as photons or light waves, not only dilutes to lower densities, but as space itself stretches to greater distances, the energy of each light wave also stretches. This causes the universe not only to expand and dilute, but to cool as well. Now, if we consider what happened to matter and radiation in the universe by running the clock backward in time, precisely the opposite conditions would occur. In the past, when the universe was younger, it would have been denser and hotter. Going further back, all the matter and radiation would have occupied a smaller volume, making the universe denser. The light that was stretched by cosmic expansion, when time is reversed, would have had its wavelength shortened, leading to hotter conditions and higher temperatures. If you imagine going all the way back, as far as the laws of physics allow, you would arrive at a singular state, where all the matter and radiation were contained within a single point of infinite density and temperature. The original concept of the Big Bang led to the formulation of 5 fundamental predictions about the early, hot, and dense conditions of the universe. These predictions became the cornerstone of the Big Bang theory. The universe should exhibit expansion, evidenced by a clear redshift distance relationship among extragalactic objects. The universe should have originated somewhat uniform, with structures like stars, galaxies, groups, or clusters of galaxies, and a large-scale cosmic web forming and evolving progressively over time. The universe was hotter in the distant past, reaching a temperature where stable neutral atoms couldn't form. This led to the prediction of a relic radiation background known as the cosmic microwave background, observable today. In the early, extremely hot universe, atomic nuclei couldn't stably form, predicting the relative abundances of light elements, hydrogen, helium, lithium, and their isotopes formed in the early universe. The universe was once so hot that neutrinos played a crucial role. This prediction was recently confirmed, suggesting that cosmic neutrinos should leave detectable imprints in both the large-scale structure and the residual radiation from the Big Bang. With strong observational support for all 5 predictions, the Big Bang theory has stood unchallenged as the leading explanation for the early universe since the mid-1960s, coinciding with the discovery of the cosmic microwave background. While evidence supporting the hot Big Bang theory was accumulating in the 1960s and 1970s, certain puzzles emerged that the Big Bang alone couldn't explain. Several observations contradicted the idea of the universe originating from a singular state of extremely high temperatures and densities. 3 of these puzzles are particularly noteworthy. First, we have the horizon problem. When we look in different directions, the universe appears to have the same temperature and density everywhere. However, since the beginning of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with each other. The question arises, how did they evolve to have the same temperature and conditions everywhere? Secondly, we have the flatness problem. In an expanding universe, there's a constant interplay between the initial expansion rate driving things apart and gravitational effects attempting to bring everything back together. In our universe, these opposing forces seem perfectly balanced, resulting in an exactly spatially flat universe. The question is, why was our universe born with these specific properties? And thirdly, we have the monopole or ancient relic problem. If the universe reached arbitrarily high temperatures and energy conditions, why are there no exotic leftover heavy relics such as right-handed neutrinos and magnetic monopoles? According to the theory, these particles should be observable and present today. Instead of simply accepting these conditions as the way the universe was born, which goes against the scientific approach, scientists seek a mechanism that would mandate and set up these initial conditions. The solution to these cosmological puzzles emerged in 1980 through a groundbreaking paper by Alan Guth. He proposed that an early, rapid, and unrelenting phase of exponential expansion, where the universe's energy wasn't distributed among matter and radiation particles, but was inherent to the fabric of space itself, via a field or some other mechanism, could address all 3 problems. For the horizon problem, the universe's having the same temperature and density everywhere is explained by the fact that, in the past, things were causally connected. This connection was stretched during the early expansion phase of inflation, leading to the observed conditions. For the flatness problem, inflation stretched the universe to such an extent that regardless of its initial conditions, the visible part appears indistinguishable from being flat today. And as for the monopole problem, the absence of ancient leftover relics is explained by inflation preventing the universe from reaching arbitrarily high energies or temperatures. The maximum temperature achieved after inflation ended avoids the creation of these relics. Inflation not only provided a mechanism to explain these observables, but also offered a powerful alternative to the standard hot Big Bang model. Moreover, as additional issues were resolved to show how an isotropic, homogeneous early universe could be restored after inflation, it became clear that inflation could serve as a quantum mechanism for seeding the universe with initial imperfections or the seeds of cosmic structure, ultimately leading to the detailed structures we observe today. In the 1980s, inflation theory made specific and testable predictions about the seeds of cosmic structure that should be observable in both the cosmic microwave background and the large-scale structure of the universe. These predictions, formulated decades ago, have been confirmed by observations made from the 1990s to the present, including a nearly but not perfectly scale-invariant spectrum of imperfections, density and temperature fluctuations, density imperfections that are 100% adiabatic and 0% isocurvature in nature, fluctuations on super-horizon scales, larger than what a signal moving at the speed of light in an expanding universe could create, a finite maximum temperature for the universe during the hot Big Bang, significantly smaller than the Planck scale. Because inflation involves exponential expansion of space rather than terminating in a singularity like the original model for the Big Bang, it paints a different picture of the beginning. Instead of an emergence of time and space from a singular state, inflation suggests a rapid whoosh leading to a Big Bang. Now, we face the profound question about the true beginning of the universe, if such a concept even applies. In the context of the hot Big Bang without inflation, we could extrapolate backward and reach a singular state where the size of the universe approaches zero in a finite amount of time. However, inflation complicates this picture. The exponential expansion it induces makes it impossible to extrapolate back to a singularity. With exponentials, reaching a state where the universe had zero size would take an infinite amount of time. To further complicate matters, the observable evidence for inflation, where quantum fluctuations generated by inflationary processes left imprints on our visible universe. This corresponds to merely the final 10 to the power of 32 seconds before inflation gives rise to the hot Big Bang. If we were hoping to postpone a singular beginning to an earlier epoch, inflation dashes those hopes. There is nothing we can observe that provides insights into what, if anything, gave rise to inflation. A captivating aspect of inflation is known as eternal inflation. When examining the details of how inflation operates, practically any model that successfully solves the problems with the original Big Bang and produces the necessary quantum effects to seed the universe with imperfections will lead to a scenario where, although inflation ends in certain regions, like our own, there will be infinitely more surrounding regions where inflation continues, generating more space that keeps inflating. In essence, once inflation begins, it erases any information about what existed before, and the inflationary state will persist indefinitely into the future. Occasionally, due to quantum fluctuations similar to those seeding the structure of the universe, there will be individual regions where inflation ends, leading to a hot Big Bang. However, these regions will be vastly outnumbered by areas where inflation continues eternally. Notably, no two independent regions with Big Bangs will ever overlap because the inflating universe drives them apart. Despite its allure, eternal inflation has its constraints. It is only eternal into the future, not into the past. In fact, it has been proven that inflationary spacetimes are not past-time-like complete and must have originated from some prior, non-inflationary, and possibly singular state. You can't evade the issue of past-time-like incompleteness by turning to alternatives like bouncing cosmologies or cyclic cosmologies, as these have been shown to face similar problems. However, this doesn't necessarily mean the universe must have begun from a singularity. While it might have, it's not a strict requirement. For instance, it's possible to construct a past-time-like complete spacetime where inflation occurs by modeling the scale factor of the universe, which determines the expansion rate as a growing exponential plus a constant, rather than a pure growing exponential. In summary, the hot Big Bang, while the best description we have of our early universe, wasn't the absolute beginning. There's a limit to how far back we can extrapolate the temperature and density of our matter and radiation-rich universe. Before the hot Big Bang, there was a phase of cosmic inflation, which set up and led to the hot Big Bang. During inflation, space was filled with energy, not matter, and radiation, and it expanded relentlessly in an exponential manner. Inflation couldn't have continued indefinitely and must have originated from some pre-existing non-inflationary state. Unfortunately, we have limited knowledge about this prior state, except for the numerous things we can confidently say it could not have been. We don't live in a universe where matter floats around in empty space. We live in a universe of energy fields that spread throughout the universe and interact with one another, creating everything we see in the process. When contemplating the vastness of nothingness, the infinite void, death, it's astonishing how the concept of nothing can evoke such fear. William Shatner, at the age of 90, embarked on a space journey anticipating to encounter the mystery of the universe, only to find there was no mystery, no majestic awe to behold. All I saw was death. I saw a cold, dark, black emptiness. It was unlike any blackness you can see or feel on Earth. It was deep, enveloping, all-encompassing. Yet, in another paradox of nothingness, Shatner wasn't truly observing a void. Rather, he was looking at a vacuum where, at that very moment, a lot was happening that he couldn't see. Quantum field theory stands as one of the most successful theories in physics, renowned for its remarkable accuracy in predicting the outcomes of diverse experiments. According to this theory, our universe doesn't consist of matter floating in empty space. Instead, it is a universe of energy fields that permeate space and interact, giving rise to everything we observe, including ourselves, as we are an integral part of these fields. Some physicists describe these fields as fluid-like, akin to water in a swimming pool, while others liken them to a room filled with varying levels of energy, much like a field of distributed heat. These fields are in constant motion due to quantum fluctuations, brief changes in energy resembling ripples in a wave, caused when external forces excite the particles within the field. For instance, an electromagnet can induce changes in an electromagnetic field. Even in their lowest energy state, known as the vacuum state, the fields exhibit continuous activity. Pairs of positive and negative particles continually borrow energy from the vacuum, briefly materialize, and then vanish, returning energy to the vacuum. These ephemeral entities are termed virtual particles. When the field is excited or reaches a higher energy point, it has ripples or waves that create elementary particles that are not canceled out. It is these particles that remain, interacting with one another, that creates the world we know. The particles created by the field are contingent upon the type of field in question. There are different matter particles, each associated with specific types of fermions. Electrons, up quarks, down quarks, fundamental constituents of all atoms, and neutrinos being examples. Additionally, these fermions interact through three types of fields: electromagnetism, which involves photons as its particles, the strong nuclear force, which features gluons, and the weak nuclear force, with W and Z bosons as its particles. According to Cambridge theoretical physicist David Tong, without fields of force, matter particles would essentially drift aimlessly in the universe, devoid of interactions and lacking any interesting behaviors. Then, there's the Higgs field, likened by Tong to molasses spread throughout the universe. The Higgs field imparts mass to other particles, preventing them from moving at the speed of light. Tong acknowledges that this metaphor is imperfect because it implies friction, whereas in reality, various particles interact with the Higgs field in distinct ways. All the fields, including matter and force fields, are present everywhere, but they interact in diverse ways. Some particles within these fields completely disregard each other, while others interact, giving rise to reactions and complex structures. The collaboration of these fields encompasses everything we comprehend and observe, as well as much that remains unknown and beyond our perception. Strangely, the creation of particles that constitute matter is an exception. For instance, an atom comes into existence when there's enough energy in the quark fields to produce quarks that aren't annulled by antimatter quarks, although the reason for this occurrence is not fully understood. Gluons, which are particles associated with the strong force, bind with two up quarks and one down quark to form a proton. Subsequently, gluons link protons with neutrons, creating a nucleus. Physicists theorize that the visible universe comprises remnants that manage to endure the constant creation and destruction of virtual particles. However, it's worth noting that the particles constituting dark matter present a separate and distinct matter. Even though the universe is teeming with virtual particles, it doesn't entirely dismiss the concept of nothingness. Firstly, there's the mystery of the nothingness preceding the Big Bang, a realm we are yet to comprehend. Moreover, the nature of this nothingness, comprising vast fields of quantum energy, appears to be something that yields a combination of ingredients, namely matter and force, culminating in the creation of our world. Physicists remain uncertain about why, following the Big Bang, certain elemental particles managed to endure. In his book, A Universe from Nothing, Theoretical physicist and cosmologist Lawrence Krauss suggested that the answer lies in the evidence. The inherently unstable nature of nothingness gives rise to elementary particles. There's also the possibility that the entire universe is just one big virtual particle. The vacuum genesis hypothesis theorizes that the entire universe began as a big fluctuation in the nothing that came before it. While it hasn't been proven, it sure is an interesting idea to think about. That in the end, all we, you, me, the whole universe, add up to is a big bunch of nothingness. No matter how vividly you can imagine an empty universe with absolutely nothing in it, that mental picture doesn't align with reality. Insisting on the validity of the laws of physics is sufficient to discard the notion of a genuinely empty universe. As long as there is energy within it, even the zero-point energy of the quantum vacuum is enough. There will always be some form of radiation that cannot be eliminated. The universe has never been entirely devoid of content, and as long as dark energy doesn't completely decay, it never will be either. The universe is the way it is, and while we endeavor to comprehend it to the best of our abilities, we must remain humble in the face of the vast cosmic unknown. The only advice I can give you is this: embrace the curiosity that drives us to explore, question, and uncover the mysteries that continue to unfold. And that's it for the video. I really hope you enjoyed it. Thanks for watching, and check out this video where we talked about a radiation that may be faster than light. It's on your screen.